All right, thank you for the introduction. Indeed, I will be talking about our verification for certain Chevalley groups. This was work done by 4 of us at, maybe if the slides go, at Carnegie Mellon University. This is truly a student work. The 2 on the left are undergraduates. They are the ones who are in the trenches writing the proofs in Lean. The student on the right, Noah, is a fellow PhD student of mine. He was the one who knew the mathematics and was the one who worked on the original pen and paper proofs, and he was the one that really drove us to formally verify this work in Lean. And then there's me. I worked on the automation of the proofs, setting up the definitions such that things work a little nicer. Noah hadn't worked in Lean before, and so I helped advise him on setting things up so that things would be nice or nice enough for the formalization that we had. You also notice that this is a picture that I took a few days ago in Reykjavik. I'm holding a cinnamon roll from a local company called Broad & Co. If you have time before you leave, please go visit. I believe it has the world's best cinnamon roll, and so do a lot of other people. So please go visit. This is not sponsored. Okay, so the title is a bit of a mouthful. There are some alternative titles for this work, including some type isomorphisms are better than others, and we will see why. Surely there's a macro for that. Parentheses be gone, and automation in need of automation. And so perhaps at the end of the talk, instead of you asking me questions, I can ask some of you questions of how to improve the automation here, because I know it can be done. A warning, I know about the math that we formalized, but not about the broader context of the mathematics, these Chevalley groups, Lie groups, and higher dimensional expanders. So if you see this warning sign or have a question about the broader maths, I probably will not be able to answer you. So please refer to the citations that we have in our paper, but I will try my best. Okay, so what do we prove? We proved in Lean that 3 specific groups can be defined using a canonically smaller set of equations than previously known. More specifically, we showed that the 3 groups called the A3, B3 small, and B3 large graded unipotent Chevalley groups presented by the weak Steinberg relations are isomorphic to those 3 same groups when presented by the full Steinberg relations. And so the smaller set of equations is the weak versus the full set of relations. And the proof strategy was basically to show that each full relation could be derived from the weak relations. And so for each missing relation, we started with the left-hand side and pushed symbols around until we were able to express things in terms of the weak relations. And so this is essentially the same as solving 1 or more group rewriting problems per missing full relation. In Lean, the statement looks something like this. So for all R relations in the full set for whatever group or system that we're working in, if you project that relation into the group presented by the weak relations, it's equivalent to 1. So that's just an equivalent way of saying what I wrote out in words on the previous slide. So why do we prove this? So the formalization that we did is based on a pen and paper proof that is on arXiv, written by Noah and his advisor, Ryan O'Donnell. And it's a little small to see here, but in the corner, the paper was 130 pages, and 80 of those pages were just these hand pen and paper calculations for these relations. And so wouldn't it be nice if these kinds of tedious mechanical relations could be verified by a computer? And indeed, the main reason why we formalized this was to verify a result involving hundreds of calculations. And these calculations were not nice in the sense that there's error terms that you can throw around or asymptotics. You had to be very precise. There were constants that had to be right. There were negative signs that you couldn't drop. And these computations really were equalities. So this is something that a computer formalization is very nice for. And Noah in particular was worried that he made a mistake somewhere in those 80 pages. And so part of the reason that he wanted to do this was to emotionally convince himself that the work is correct. And indeed it is. We also wanted to lay the groundwork for similar verifications in the future. Of course, this is a common thing for formalizations, but besides these 3 groups, there's whole families of these groups. And so if you start with a certain set of definitions in these formalizations, maybe you can adopt the setup or the automation to find solutions to these problems in groups that haven't been studied before. And there's lots of future work left. So I work on this problem in particular, and note the warning sign. This is the math that I do not know. So the ultimate goal is we want to construct topological objects called higher dimensional expanders. And the story that Noah tells me goes like this. Suppose we want to construct a higher dimensional expander. The only known nice way of doing that is to use these things called simplicial complexes. I don't know the details of what a simplicial complex is, but you can see a picture that looks like this. It's composed of n-dimensional triangles, like intersections of faces and such. So you have points, lines, triangles, tetrahedrons, and so on. And you can study how these things behave in higher dimensions, their connectedness, their topological properties, what happens if you take just a lattice of these things. And so if you have some nice simplicial complexes, you can study them and construct higher dimensional expanders. Currently, there's only two known constructions of these things. The first go through quotients of Bhoja T buildings, and the other is through coset complexes. And that is where these Chevalley groups come in. If you find Chevalley groups with a good set of these relations, these Steinberg relations with nice properties, then you can build the coset complexes to build the other complexes to build the expanders. Yes?
The simplicial complexes that you consider, they may be infinite?
I don't think so. The ultimate goal is to get a maybe like a parameterized family of these expanders. So for any n, you could build something like this. So in that sense, I guess they're infinite, but for any particular expander, you want a finite object. And so of all this story, we only formalized the part in blue, that we found that the groups have these good sets of Steinberg relations. But this is how it fits into the wider context. The higher dimensional expanders are useful for quantum error correction, local property testing, and they're just interesting objects from a higher dimensional geometric perspective. So that's the theoretical computer science motivation for why we might want to study these things. We also want to do basic research in group theory. The result that we proved is just interesting on its own, that you can define these groups using a smaller set of these relations. It more tightly characterizes the group, I suppose. So what are Chevalley groups? They're similar to Lie groups. They're defined on square matrices where the elements of the matrix are field elements. This could be just drawn from a background field, or it could be polynomials in a univariate. And they express nice symmetries and geometric properties, and in fact, the things that we focus on here relate the algebraic group properties to the geometric properties of some underlying vectors. And so there's a fact that says every Chevalley and Lie group can be generated from a set of generators comprising vectors and field elements. And group multiplication on these generators corresponds very closely to the geometric properties of the vectors. So in our paper, these generators look like this. They're either pairs or triples. The zeta here is a root vector as part of a basis or a system. And the t is a field element drawn from some background field. Often we'll write fq, where q is a sufficiently large prime power. And then in the triples here, we have a degree. This corresponds to the highest degree or the cap of the degree of a monomial for a polynomial in T in a univariate. It's not too important what the degree is, but you can essentially think of it as an additional parameter that gives us more space or more structure to work with when we're constructing these coset complexes. And it's very easy to put this in Lean as a structure. You can see each of the fields represented here, as well as the hypothesis that the degree I is no more than a certain value. In this case, it's the height of the root vector. You don't need to worry too much about that, but we can encode this quite easily. So these generators have some nice properties. So for instance, they express a linearity property. So if you group multiply these two generators together and they share the same root and the same degree, then their field elements add, or group multiplication commutes with field addition. You have the identity, where if you have a field element of 0, then you have a group identity of 1. And inverse. If you take the inverse, then you can pull the minus sign into the field. You also have a set of commutator relations. So the commutator I put in the top right. For any group, the commutator of A and B is AB, A inverse, B inverse. And if A and B commute, then the commutator is 1, because you can put A and A inverse together and B inverse together and get back the identity. But if A and B do not commute, then the commutator is a measure of the error, what additional term you need to add if you commute A and B. And as it happens, for any pair of roots zeta and eta, the commutator of these two generators is a product of other generators of the form that's written here. And the fact that you can do this is, Noah describes this as being a minor mathematical miracle. In particular, the product might involve only one or two terms, whereas if you were to take the underlying matrices and multiply them, you'd have 3 multiplications. You get a simplification of the matrix multiplication if you use these relations here. And as far as I know, these Chevalley constants, C, zeta, eta, AB, don't follow any sort of pattern. They're very hard-coded in our formalization, and it seems like you have to hard-code them. I don't think there's any sort of function you could write aside from a piecewise, like case 1, this is what it is, case 2, this is what it is. So that's why the constants were very delicate in these computations. And so these are some of the Steinberg relations that appear in our paper. There are others, depending on if you're in the weak or the full system, but these are the easiest to understand and the examples that I'll be using in this talk. Okay, so what's a presentation? So when I say that we can define groups with these relations, I mean that you can specify them with a presentation. And so roughly a presentation is a string rewriting system where you have a set of symbols, these are the generators, and you take these modulo the set of relations, which are also strings using these symbols. And the identity element in this string rewriting system is the empty string, and the group operation is string concatenation. And so some examples include, suppose you have the symbol x and its inverse x inverse, and your single relation is x to the n. This corresponds with the integers mod n under addition. So if n is, say, 5, and you have x to the 3 and x to the 2, then when you add those together, that's equivalent to the empty string, or the identity. Similarly, if you have 2 symbols x and y, and your relation is the commutator, this is a commutator relation, then this is equivalent to addition of x and y separately, where the canonical way of representing a string is to put all of the x's in front and then all of the y's, because if any y appears before x, then you can left multiply with this commutator relation and reduce it and end up with x and y. And so presentations give a very succinct way of specifying groups, and as it happens, this is the nice form that we put these Steinberg relations in when we're looking at these Chevalley groups. An equivalent definition of a presentation is written here, and this is the definition that appears in Mathlib. So this is the one that appears in our formalization, but I guess more intuitively you can think of it as a string rewriting system. Okay, so when at the start I said that for each missing full relation, we derive them in terms of the present weak relations. So what does one of those calculations look like? It looks like this. So assume the weak Steinberg relations. These include those linearity and inverse and commutator relations and others. And then we want to show this one. So we want to show linearity for the root beta plus psi plus omega, such that t and u will add under group multiplication. The proof looks like this. Compose I, the degree, arbitrarily into I1 and I2. Then we proceed by symbol pushing. So we start with the left-hand side, and we have a relation that allows us to decompose generators on larger roots in terms of smaller ones. And so in this case, it's very much a commutator relation. You have A times B times A inverse times B inverse, where the inverses have been pulled into the generator. And then we have relations that allow you to commute this 3-vector generator around the smaller elements. And then we can decompose that as well. On the left, you can use linearity to combine those two. And in the middle, you can use linearity to combine them to get 0 in the field element. And as we know, 0 in the field element gives us the group identity 1, so we can drop that. And if we do, the betas on either side will also be able to be combined via linearity. And then we end up with one of those, the inverse direction of the commutator relation, where you have A times B times A inverse times B inverse. And so we're able to recombine back into the form that we want. And so almost all of the calculations in our formalization look like this. And so in some sense, we could have used an automated theorem prover or a specialized decision procedure to find these proofs. But Noah did them on pen and paper first. And so then we used his that he found. But you can imagine in the future you could write a decision procedure to do this sort of thing. It doesn't get any easier in Lean. This is the same proof as it appears in our formalization. And each of the lines that were on the previous slide appear as a particular rule that we invoke here. So even though we have some automation lurking around, we still have to do step by step like it does appear on pen and paper. This actually isn't how it appears. It looks a little more ugly, but I prefer this form. Okay, so the proof strategy is, as I said, all the proofs look kind of like that calculation. There is some a broader strategy at work. I'm not going to go into the technical details, but there is some symmetry in the problem. You can relate some of the missing roots to others via some property called reflection, and so you may only have to do half the proofs for some roots. But largely, you take a missing relation and you decompose it and you symbol push and you get what you want in the end. Some proofs are worse than what we saw. So you can't sometimes just parameterize across the degree. You have to case on the degrees. And so each of these is a separate lemma that symbol pushed in the way that we saw, and then you combine them all together for the more general form. Sometimes it gets better. I already spoke about reflection. So we proved one half of these theorems, and then we have a macro that unfolds and uses this reflection property to prove the other half of the relations. Okay, so what are some design decisions that impacted our work, made it easier, or maybe got in our way? So first, we have to define the roots of these generators. And so in the paper, we work with these things called root systems. You take a small set of these roots called a basis, and that basis defines a larger system called a root system. So here we've been mentioning alpha and psi. These are using the standard basis for R3 is either E2 minus E3 or E3, and there are others. In particular, these roots have to be either short or long. Short roots have a single plus or minus coordinate in the whole vector, whereas a long root has 2 plus or minus 1 entries. And so taking the system with a modulo 2, you're constrained in the kinds of roots that you can add. And so you could see that if you take the span of these vectors, you might expect 2 beta to be one of our vectors, but 2 beta wraps around to 0. So this is, if you take the vectors on the left and you take their non-negative span in this kind of modular system, this is the set of vectors that you can create. And so in Lean, we had to manually define these roots because if you just have these vectors, you'd have trouble defining addition. You'd have to have an option result, perhaps if the addition is not defined, or you have to carry around a hypothesis that the 2 roots are okay to add in the system. And so we just do the maybe straightforward but a little dumb thing of writing out each of these roots in particular. And so if you need to write down a relation with like a plus, you just use one of these symbols here. This also means we have to hard code in some other things. So there's a property called height that I mentioned earlier. This essentially says how many instances of a root vector appear. And so we have to hard code this in manually. The advantage of this is that we're never wrong. These roots are all valid, and Lean will yell at you with red squiggle lines if you ever put in the wrong root. But the disadvantage is you lose some of these nice vector properties. You don't automatically get that beta psi is beta plus psi. These are just symbols in an inductive type. So there's some pros and cons here. And I think for a beginner to Lean, and with all the proofs already found, that this was a more straightforward option. But if you generalize, you probably want to move away from this. And so this is some type isomorphisms that are better than others. Okay, we have macros to help simplify the process. Many proofs were the exact same, differing only by the root or the degree. So for example, this linearity thing holds for all roots zeta, so it would be nice if there was a macro that generated those theorems. Similarly, if you have a commutator that looks like this holds for a lot of smaller roots. And so the solution is we wrote macros that just expand into the theorem body and the theorem statement using a consistent naming scheme. So this is basically the start of our file. We just run through the roots for which these theorems can unfold nicely and just list them all.
What's wrong with the for all quantifier over your inductive?
Right, that's a choice for the roots that the way that we defined roots here. At the end, we do want to show that like linearity hold for all these roots. But you can only derive linearity for the larger roots in terms of the smaller ones. So you don't have, at the end you have for all, but in the middle of proving them, you only have access to the first 6 or so. So these are the 6 trivial ones. but you have to prove by hand the missing ones. So yeah, we need to another problem is we need to declare the macros for each root system. I'm passing in f directly, and these macros declare B3 small, declare B3 large, or so on, are specialized for the root system. I essentially want a macro to create other macros, and that's my question to the audience, is how to do this. Another pain point that we had are parentheses. They get in the way. Suppose we want to commute two terms that are not in the same set of parentheses. So we have something like this. This is obvious if we're in an abelian group. We just commute B and A. But in lean, if you try to do this, you find that A and B are not together in the same set of parentheses. It's associated incorrectly. And so how do you do this without manually having to reassociate every time? And so the answer is you borrow a technique from the category theory library and specialize it for groups and throw it into a specialized group rewrite tactic. And this decorator that takes in terms then essentially reassociates things in a nice way. And so if you try to commute A and B here, using normal rewrite, it'll fail, but group rewrite in our system will try it, see that it fails, and then try the other associated version. So this sped up our proofs. Another benefit is we can combine with a specialized simp decorator or procedure to help simplify things. So we saw previously that we had this identity element in the middle. Group rewrite will automatically reduce that down to the identity and then remove it, which will help simplify those steps that mathematicians do just naturally. So this is what I mean. Group rewrite and Chev simps will simplify down to the identity element. Some other pain points. Presentations, the way that presentations were defined in lean versus how we work with them in the equational form. So the commutator relation is stated like this. So perhaps these two elements commute, but when we work with them in a theorem, we really want to have the four things multiplied out, or we want to say that the left equals the right in this form. And so pretty much anytime we have a commutator in the top, we have lemmas that say the middle, the bottom two forms, and we're converting between them. So we have macros that automatically generate these, but we do need to have things in the form that we want at any point we're in a theorem. Group and field arithmetic often needed massaging to discharge with the automation tactics. Often this involved the number 2. So here's a snapshot from the middle of one of our theorems. We want to prove that 2 times u divided by 2 times t is equal to u divided by t. Of course, as long as 2 does not equal 0. And in fact, in this case, 2 does not equal 0. But the automation won't get you all the way. You have to sort of finagle with it. And so there's lots of these little identities that automation won't discharge that you need to move around a little bit. Maybe the automation has gotten better. I don't know. So that's a quick tour of the formalization. There's lots of technical details that I've left out, but I hope I've convinced you that we have a little bit of automation that helps things along, and it was mainly just symbol pushing for a nice group theory result. So thank you for your attention. Happy to take questions.